Cosmology Supplement 5, Olbers Paradox. Why is the night sky dark? Hello, welcome to this short supplement on Olbers Paradox for the Expansion of the Universe course. The lecture script is available at a link given in the description of this video. Why is the night sky black? If your response is, well, duh, it's nighttime, I would ask you to give it some thought as a scientific exercise. Different people throughout history have thought about why the night sky is black, not bright. In the 6th century and the 16th century, Kepler in the 17th century, Halley in the 18th century, and Kelvin in 1901. But we now call this Olbers paradox after Heinrich Olbers, who described the problem in 1823. Let's see what we can make of this. We will make a number of assumptions as though we were thinking about this with the limited knowledge of the universe available, say, before 1910. As we identify each assumption, ask yourself whether it is true or not from what you have learned in the main course. Assume the universe is infinite in size and static, unchanging. Assume that the speed of light in vacuum is finite, constant, unchanging. Halley, Kelvin, and Olbers were aware that light has a finite speed and were aware of the approximate speed value. Assume the universe is infinitely old and unchanging. Assume stars are infinitely old and shine at the same luminosity for all time. Assume that no dust blocks starlight from reaching us. Assume that stars are uniformly distributed throughout the universe, an infinite number of stars. Assume either that all stars have the same absolute luminosity and color, or that we can use an average luminosity and color. Assume that there are n stars per unit volume, in whatever units, and that each star has luminosity L throughout the universe. Specific numbers won't matter much in this video, but for concreteness, we will assume 1 billion stars per cubic megaparsec, about 100th the number density for our local group of galaxies, with an average luminosity of 5% of the sun's luminosity. For any direction you look in the night sky, ultimately there is some star shining, sending its flux to your eyes, though it may be extremely distant. We're assuming this. First, we'll do the calculation using a flawed approach, but we need to see why the approach is flawed. We will sum up, integrate the light flux that reaches us from all the stars in the universe. We consider our position to be the origin of the universe, and we will use spherical coordinates. We won't care about angles, just the radial distance from us to the stars. We divide up the universe into thin spherical shells centered on the origin. The distances will be so large that don't worry whether the shell is thicker or thinner than a star. The volume of the shell is 4 pi r squared dr. We're assuming a static Euclidean space. The number of stars within the shell is n times 4 pi r squared dr. Well, We can use this for distances that are not too close to the origin. We are taking discrete stars and using them in a continuous manner, but it turns out that this is not the crux of the paradox, so we will continue. Now we need the flux received at the origin from a given distant star. The flux of one star is its luminosity divided by 4 pi r squared. We're assuming static Euclidean space. Now we need the flux received at the origin from all the stars in a single shell. The flux from the stars within the shell equals the flux from one star times the number of stars within the shell. When we do this, the factors of 4 pi r squared in the numerator and the denominator cancel. We end up with a constant amount of flux from each differential shell. When we integrate this from some distance to infinity, we assume the universe was infinitely large, we get infinite flux at the origin. We did something wrong. We did not take into account that the star has finite diameter and is opaque. It blocks the light from stars directly behind it. We overcounted the flux. Let's try a different approach. We look in some direction, this direction, and imagine how far from us will be a star, this is a star, along our line of sight. See, our line of sight is hitting this star. If the average radius of stars in the universe is r sub star, and the distance from us to this first star is w, then the volume of the cylinder to the first star will contain exactly one star's center, this star's center. The volume of the cylinder that contains the center of one star times the universe's number of stars per unit volume will equal 1. We then calculate the distance w from the average star radius and the number of stars per unit volume. If we assume 1 billion stars per cubic megaparsec and an average star radius equal to the sun's radius, we get a distance of 2 trillion light years. This light takes 2 trillion years to reach us. An average star is probably smaller than the sun, and the distance and time would be even larger. The flux reaching us from that single star is quite small. Here I used a luminosity of 5% of the sun's luminosity. But our eyes are receiving flux from a spherical surface of radius w with luminosity L. The angular area in the sky of the single star is given here. This surface brightness, calculated here, would be 400 trillion times the brightness of the night sky between Milky Way stars. The night sky would be almost as bright as the sun. So, Olbers' paradox is that simple assumptions lead to a night sky that would be bright with light, but clearly the night sky between the Milky Way stars is black, not bright white, yellow, or red. One or more of our assumptions was wrong. Most of our assumptions were wrong, but each has different impact on the result. The speed of light is finite, constant, and unchanging. We don't know whether the universe is infinite in size or finite, but it turns out this is not the real issue with the paradox. The universe is not infinitely old. Our observable universe had a hot Big Bang origin. We can only see light that was emitted after our Big Bang origin. Since light has a finite speed, we should not have integrated to infinite distance, even if the universe is infinitely large. We should have stopped integrating at distance equal to the speed of light times the age of the universe. So 13.78 billion light years, which is greatly less than the trillions of light years required for the night sky to be filled with starlight. Referring back to the cylinder example, pointing the cylinder in different directions, only 1 out of 100 trillion directions has a star to send flux in our direction since stars formed. The finite age of the universe is the chief factor for why the night sky is dark. Interestingly, the writer Edgar Allan Poe in the mid-1800s wrote of finite age as a reason the night sky would be black. Actually, in every direction we could see the cosmic microwave background. In that microwave range, the sky is not black, though water molecules in the atmosphere absorb microwave radiation. Olbers' paradox applies to starlight and the visible range, not the microwave range. Stars are not infinitely old. The oldest stars began to shine 50 to 400 million years after the Big Bang. Many stars are much younger, many stars died out, though the average star is still shining. So we should have stopped integrating at somewhat less distance to account for the age of an average star in the universe. The universe is not static and unchanging. The universe has been expanding since the Big Bang. In our expanding universe, the flux of light from distant galaxies is much less than the 1 over r squared formula would give. So the night sky would be even darker. And the light from distant galaxies gets redshifted. So some of the emitted visible light is no longer visible when it reaches us. It is infrared. So to our eyes, the night sky would be even darker. Stars are not uniformly distributed throughout the universe. Stars form within galaxies and shine from galaxies. The stars our eyes see in our night sky are all Milky Way galaxy stars. In most directions in the sky, our eyes see blackness in between the Milky Way stars. Trillions of distant galaxies have not equaled the flux of our local stars. Suppose we could remove all the Milky Way stars and just look at the flux coming from other galaxies. The nearest large galaxy to us is Andromeda. Andromeda is about 6 moon diameters long in our sky, but unlike telescopes, our eyes only see a small blur at the core. Light from galaxies behind Andromeda can reach us through the gaps between Andromeda's stars, except when absorbed by a dusty region. Why isn't our night sky uniformly as bright as Andromeda's core appears to our eyes, which seems as bright as a middling Milky Way star? The next distant galaxy as luminous as Andromeda is a deal further away. Galaxies are not uniformly distributed in space. Galaxies collect in clusters and superclusters. Superclusters aggregate in cosmic filaments bordering huge galactic voids. The night sky is not as bright as Andromeda's core. Astronomers measure the black level of the sky not pointing at galaxies. This is called the cosmic optical background, or COB. Ground-based telescopes are useless for this due to light pollution and dust in the atmosphere. The Hubble Space Telescope is not ideal for this, as the entire inner solar system is bathed in a low level of reflection of the sun's light off of planets, moons, asteroids, and dust. The New Horizons spacecraft, now far past Pluto, has taken some cosmic optical background measurements of the universe, which were 10 times darker than the darkest that Hubble sees, which is darker than observed from the ground. New Horizons measurement is 30 to 60 times dimmer in the visible spectrum than the cosmic microwave background is in the microwave spectrum. So now, when someone says, duh, it's nighttime, you will have given this some scientific thought with knowledge of the expansion of the universe.